Welcome to this presentation on GCSE chemistry, with a focus on AQA exam-style questions. We will explore the questions focused on the topic about chemical changes, specifically on energy bonding and properties of substances from the 2023 Higher Tier Chemistry paper. I'll guide you through the answers step by step and explain how they align with the marking scheme. Question 4. This question is about hydrogen and compounds of hydrogen. Figure 3 shows the displayed formulae for the reaction between hydrogen and chlorine. Table 4 shows the bond energies. Sub-question 4.1. Which expression shows how to calculate the overall energy change for the reaction in Figure 3? Use Table 4. Tick one box. And you have 4 options to choose from. So this question refers to calculation of bond energy in a chemical reaction. Now, let us review the key points regarding this topic, which involves calculating bond breaking and bond formation, which are fundamental concepts in chemical energetics and thermochemistry. If we want to break a bond, we have to put in energy, and this is called an endothermic process. An example of endothermic reaction during which energy is absorbed is photosynthesis. First, plants absorb sunlight to convert carbon dioxide and water into glucose and oxygen. Therefore, the reaction requires energy from the sun to break the bonds in carbon dioxide and water. Since energy is absorbed, this is an endothermic reaction. On the other hand, when new bonds form, energy is released. This is called an exothermic process. Let's look at a real-life example: the combustion of methane. When methane burns in oxygen, it releases heat and light energy. Bonds in methane and oxygen break, and new bonds form in carbon dioxide and water, releasing energy. Since more energy is released than absorbed, this is an exothermic reaction. Now, to calculate whether a reaction gives off heat or absorbs it, we use the following equation. Energy change equals energy needed to break bonds minus energy released when forming bonds. If the result is negative, the reaction releases heat and it is exothermic. If the result is positive, the reaction absorbs heat and it is endothermic. In our question, the reactants in which bonds are broken are hydrogen-hydrogen with bond energy of 436 kilojoules per mole and chlorine-chlorine with bond energy equals 346 kilojoules per mole. Therefore, the total energy required to break the bonds is 436 plus 346 equals to 782 kilojoules per mole. Now, the products in which the bonds are formed are the 2 hydrogen-chlorine bonds, so total energy released equals to 2 times 432 equals 864 kilojoules per mole. Now, to find the correct expression for energy change, we will use the formula. Energy change equals energy for bonds broken minus energy for bonds formed. Therefore, energy change equals 436 plus 346 minus 2 times. 432 equals negative 82 kilojoules per mole. It is negative, which indicate an exothermic reaction. Thus, the correct answer is 436 plus 346 minus 2 times 432 kilojoules per mole, which correctly follows the bond energy calculation method and aligns with the marking scheme. Sub-question 4.2. The reaction between hydrogen and chlorine is exothermic. Explain why this reaction releases energy to the surroundings. 2 marks. As we reviewed previously, breaking bonds requires energy, and forming bonds releases energy. In our reaction between hydrogen and chlorine, more energy is released when new hydrogen-chlorine bonds form than is needed to break hydrogen-hydrogen and chlorine-chlorine bonds. Specifically, the energy released of hydrogen-chlorine bonds of 2 times 432 kilojoules per mole equals 864 kilojoules per mole is greater than the energy needed to break the bonds of hydrogen-hydrogen. And chlorine-chlorine of 436 plus 346 equals 782 kilojoules per mole. This excess energy is transferred to the surroundings, making the reaction exothermic and resulting in a negative overall energy change. And this aligns with the marking scheme, which states to mention both bond breaking and bond forming, and explain that more energy is released than absorbed. Sub-question 4.3. Figure 4 shows part of a reaction profile for the reaction between hydrogen and chlorine. Complete the reaction profile in Figure 4. You should label the activation energy label the overall energy change. 3 marks. We've seen in the previous question that in this reaction between hydrogen and chlorine, the bond energy of reactants is bigger than the energy of bond forming in hydrochloric acid as product, so the curve will be drawn at a lower level than the reactants. And you earned 1 mark for this. Then the peak of the curve always indicate the activation energy, earning you the 2nd mark. Whereas the overall energy change is the difference between reactants and products on the energy axis, and you add the label for that. This contributes with 1 more mark to your total score of 3 marks. Sub-question 4.4. Draw a dot and cross diagram for a molecule of hydrogen chloride, HCl. Show the outer shell electrons only. 2 marks. Hydrogen has an atomic number of 1, so it will have 1 electron represented by 1 cross, and chlorine has an atomic number of 17, which means it has 7 electrons represented as dots in their outer shell. A single shared electron pair forms a covalent bond between hydrogen and chlorine. Now, chlorine has a full outer shell of 8 electrons. This helps you achieve full marks as shown on the marking scheme. Sub-question 4.5. Figure 5 represents molecules of methane and of polyethene. Methane is a gas at room temperature, but polyethene is a solid at room temperature. Explain why methane and polyethene exist in different states at room temperature. 4 marks. Let's have a look in more detail at methane and polyethene structure to understand the bond strength and energy. Methane is a small, simple molecule with a tetrahedral shape. It consists of 1 carbon atom that forms 4 single covalent bonds with 4 hydrogen atoms. These covalent bonds are strong, ensuring the stability of the methane molecule. Polyethene is a large polymer composed of repeating ethene units linked into long chains. Each carbon atom in polyethene forms 2 single bonds with other carbon atoms and 2 single bonds with hydrogen atoms. However, the intermolecular forces between methane molecules are weak London dispersion forces, which means little energy is required to separate the molecules. As a result, methane exists as a gas at room temperature. Unlike methane, which is a small molecule, polyethene is a giant macromolecule, meaning its intermolecular forces are much stronger. These stronger forces between the long polymer chains require more energy to overcome, making polyethene a solid at room temperature. Now we can write our answer about the key structural difference between methane and polyethene lies in their size and intermolecular forces. Methane is a small, nonpolar molecule with weak dispersion forces, causing it to be a gas under normal conditions. This matches the marking scheme's requirement to mention small molecules, weak intermolecular forces, and low boiling melting points. In contrast, polyethene is a large polymer with long chains, leading to stronger intermolecular interactions, which make it a solid. This aligns with the marking scheme's focus on larger molecules, stronger forces, and higher boiling melting points. By covering these key points, our answer meets all the marking criteria and ensures full marks. That's it for today's exam-style question breakdown. Keep practicing, stay confident, and you'll master these in no time. If you have any tricky questions, drop them in the comments and I'll be happy to explain. Don't forget to like, subscribe, and hit the bell so you never miss a new video. See you next time.